So, good night. Today I'm going to talk about cosmological impact of CMB data temperature measurements on constraining cosmological models. So, to start, let's talk about some basics. So, first we'll talk, so just a note about redshift. Redshift is when we all know that stars that are far away, they emit a certain light that if we know about a little bit enough about a star, you know what's the light that it's supposed to emit, if it has helium, hydrogen, something like that. But what happens is that if the light is far away, an unusual thing happens. The light that comes to us is a bit redder than expected. So the redshift is actually a measurement that defines the shift of the light emission that we receive compared to the one that it's supposed to be if you are close to the star. So just to clear annotation that so this is the calculation of a redshift, so we clear. And this is just a notation that we'll use for this presentation, that omega something is talking about the relative density of that thing. So for example, here below we have omega m, it's omega matter. So it's the density of matter in the universe. So that is clear. So just a note also, when you have a zero, it's the current value. So for example, here below, the temperature now, of the temperature of the universe now. But just to clear some things here. First, we have this is called the Hubble parameter. And it measures how the universe is accelerating, because A is a scale factor. You can see here it's calculated to the redshift also. So yeah, Hubble parameter, it calculates, it's a parameter that tells us how the universe is expanding or accelerating or decelerating. For our calculations also, it's useful that we all don't have dimensions. So we also define E, that is a function of E over H. It basically has the same meaning of H, but is dimensionless, so our calculations are easy. So a note that I have to give here, we will consider that the density of radiation in the universe, it's negligible for our models. So we don't complicate too much the calculations. And also, whatever you look, the universe is homogeneous and isotropic. So I'll talk about lambda CDM now a bit, so you understand how models work in general. Lambda CDM is the most acceptable model now that we have, and the E function is given by this. And this comes from the assumption that the universe is flat. That comes from the assumption that the universe is homogeneous and isotropic. And we also know that the temperature of the universe in lambda CDM is given by this function. Also, it's lambda CDM because lambda accounts for its dark energy. And in lambda CDM, dark energy is a constant that is constant through the entire history of the universe. What we'll see is that usually when dealing with these models, people will make alterations to E specifically and compare it to lambda CDM. But the difference here is, if you have a different model, the function of T changes too, and can help us constrain models to see if they are good or bad. And usually models divide by two categories. One, where they just a parametric extension of lambda CDM, which just adds a parameter or subtracts or something like that. Or they can be totally different, no parametric extension, and relying instead on different physical attributes. So they are describing dark energy in a different form. Or they can be a mix of both. So now I'll just talk about a bit of the data that we will use. We'll use type A IA supernova. This is usually used because, firstly, it occurs in systems of binary stars. When one of the stars collects mass from the other and becomes a supernova when it cannot handle it anymore. And it's a specific type of supernova because we know the peak luminosity is supposed to achieve. And as the same reasoning of redshift, if we know the supposed peak luminosity that is supposed to give, if we receive one that is shifted a bit to the red, we know the distance of the supernova. The supernova data originally is 1048 supernova data set, but it's compressed to 6 correlated measurements. This is used really often because it's really good to constrain omega matter. So we'll also use measurements of the Hubble parameter. That is a combination of two. There are 38 Hubble parameter measurements that combine cosmic chronometers and the baryon acoustic oscillations. First, cosmic chronometers, they rely on evolving galaxies. They amount for time, we'll say it like that. And the baryonic matter of the universe is like, first, baryonic matter is our matter. When we say omega matter, we are including dark matter. Baryonic matter are protons, neutrons, electrons, something like that. And the baryonic acoustic oscillations are the fluctuations of the matter that we see. So they are good measurements too. Hubble parameter and the supernova parameter, will refer to them as the cosmological data set, that we will compare it to the CMB temperature data set. The CMB temperature data set, it comes from like firstly, CMB is cosmic microwave background temperature. So it's from the radiation of the beginning of the universe. It comes from two data sets, one that uses the thermal CD effect and one that uses spectroscopic measurements. I'm not going into much detail here because they are a bit complex, so leave it like that. So now we are seeing how the CMB temperature can constrain models just as good. We're trying to see if they can constrain just as good as supernova and Hubble parameters constrain models. So first, we'll see one model. This is the steady state torsion model. Is one of is an extension of Einstein's general theory of relativity that includes a space-time torsion. Although it supposedly is a good alternative to lambda CDM, it's all observationally ruled out. So now we are giving it two new parameters. One is they are always dimensionless, so our calculations are easier. So one is how much the torsion affects the expansion, and one is W, that is an equation of state parameter, and this is just a function of the density, you know. And we can see here that we have this constant of torsion instead of dark energy. This is to rule out the dark energy. It's trying to justify the acceleration instead of dark energy is to torsion, and the torsion is given by lambda. So if we use these equations with the data that we have, we'll get this first. If in case of W equals 0, so it's a easier case to first see. We can see now that lambda wants to be close to 0, and omega n is around 0.3, somewhat like that, which is somewhat what it's supposed to give. We can see if lambda equals to 0 in the equations of this model. It's easier to see in the temperature formula. It gives us, again, lambda CDM. So this model to lambda equals 0 is not that much innovating. So, but now we can see with W not fixed, we can see also Now, omega m is not as well constrained because we have an parameter, but lambda wants to be again close to 0, and W it's somewhat relatively small. So yeah, but they are, especially lambda is still really well constrained with these data sets. We can now see a different model. This is the dynamical dark energy model. This is a phenomenological model in the sense that it's not driven from an action. It stems from the possibility of a time-varying light velocity. This is a particular type, so that's it. So here we have a new parameter. Although it seems like it's two, it's only one. Epsilon is just a constant because this is the values for now. It's a Hubble parameter now, and so it's just a constant. Here we only have beta. That is, they want to see it's like a scale factor for the universe. Actually, if here alpha has dimensions of minus a second, the inverse of a second. So that's why we time it by the time to have a dimensional beta. So we will now also consider first where a model, there's no cosmological constant. They here want to explain it as first a no cosmological constant, but we'll see rapidly that even with that, they come to a flat lambda CDM. We can see now that beta also wants to be close to 0, and omega is a bit off here. But if we take the beta value to the function of the temperature, you will get again lambda CDM. So the exponential cancels out, and we have lambda CDM. And this is a case where we are not adding a cosmological constant. So in this case, we have the model, and we are adding it a possibility of having a cosmological constant. So what you're seeing now is a hybrid model that is the two cases mixed. So here again, beta wants to be close to 0. And this is the new expression for the E, because now, again, this always assuming a flat universe. So this is the new expression of V. So we can only use beta because we can write the cosmological constant in terms of beta. So we only have beta again, and the omega matter is a bit more what it's supposed to. So this gives us a sign that it needs a constant there. So we also see now energy power, momentum power gravity model. This is another alternative to a cosmological constant to explain the acceleration of the universe. Here we have a bit of more complicated model because here we are explaining it. We are changing the tensor of energy momentum, which gives us the curvature of the universe. So this model is trying to explain the acceleration through curvature. So now, assuming a flat universe again, it's a small curvature because so we can assume this, and Q, and it is a scale factor that determines the strength of the modification applied. So why? Because n is the tensor at the n is a power 2. So imagine t power 2n. So all larger is the n, larger is the implication of that tensor. So Q is just a generic parameter. It's easier to do the calculations with Q, but Q is it's dependent only on n. The other ones are constants. So and just again, we are adding it a cosmological constant to have again an hybrid model. And this is assuming two things in this model. First, that it's ordinary matter, and that we have standard radiation. In this energy momentum power gravity model, firstly, you can see that n wants to be near zero again, and that omega matter is again close to a bit to the left of 0.3. And if we pick up n and put it in the equations, here you can see it's clear because this is another function that we have to do a derivative of, so it's not as visual. But you will see that this also gives us lambda CDM. But this model is well constrained by this data. That's one of the things that is important. That here the temperature data is giving it a really well constrained n. You can see how the peak is, it's really well constrained. So we can also see here that in this model, we are now considering that in this there was no cosmological constant. Here we are having a cosmological constant, so it's clear. And here the cosmological constant is around 0.7. That is supposed to, if you consider that the majority of things in the universe are dark energy and matter, including dark matter and baryonic matter, excluding radiation, if you have a omega matter close to 0.3 and the dark energy, the density of dark energy 0.7, you have one which is the density of the whole universe. So these results make a bit of sense. So that proves that our calculations are correct, but again, n wants to be close to zero. So this also shows us that when there is a cosmological constant, the n is not so well constrained, maybe because it's more neglectable. So, but that's the results that we have for this model. This model is still in works because we can also do it with no ordinary matter. So the equations will change a bit to more complicated things with other functions, but we can also consider that the radiation, it's not standard radiation, that the radiation is changing, is different than one third. That is what we use here. So yeah, that's what we do. But the conclusion is here you could see the models were not giving nothing out of the ordinary, but with the parameters that we have, first they were giving almost all the time on the CDM, and after we could see also that using the temperature data, our parameters were getting really constrained, really good peaks. So the temperature the CMB temperature is a data set just as good as Supernova, and has a lot of possibilities because now it's not as well used as the Supernova and other parameters that include cosmic chronometers and baryonic oscillation measurements. So yeah, that's it.